be sunk on again after all these years. I had originally planned to give a talk that would have fit with an algebra seminar, but I thought for the colloquium it would be more fun to talk about something I learned when I was visiting India the last few weeks. So I was talking with Manjul Bhargava, and he told me a story about Indian music. So that's the source of the title. So I'm going to write down the title here. Story, I realized it related to some work that I'd done a few years ago with Kurt Wilf and Carl Sanders. So let me tell you about what Bhargava told me about Indian music. So one form of music involves just two kinds of notes. You have a short note, which is one beat, which we can represent by a square, and then a long note, which is two beats, which is, well, it's a Raga. So the natural question you might think of is, if you want to fill out n beats, how many ways can you do that with short and long notes? How many ways? Beats. With short and long notes. So each such way of doing that you could call a Raga. So each such is a Raga. While I was in India, there was a classical Indian performer who performed quite a few ragas, and actually what they would do would be systematically to work through all the possible ragas of a given length. So let me write down a couple examples. If n is 1, well, there's only one way to do this. You have to use a short beat, and then the number of ragas is just 1 in that case. F sub 1 is 1. Now if you look at n equals 2, well, you can have 2 short beats or 1 long beat. So F2 is 2. N equals 3. Okay, well, you could have all short beats. You could put a long beat first. Let's put a short beat. And or else you could put a short beat followed by a long beat. Maybe to try to distinguish the shorts and longs, I'll shade in the longs. So F3 is 3. Okay, so there's a reason that I'm using F as a notation. I understand there's a lot of people here interested in combinatorics. So the natural number, the number of ways of doing this is Fibonacci. So the answer is the number of ragas of length n is the n Fibonacci. So, in fact, the reason that this is true is quite simple. That if you look at the recurrence formula for that Fibonacci number, it's just that this is f of n minus 1 plus f of n minus 2. Okay? And all you need to do is to think about following scheme. If you're trying to count ragas of length n, you just look at what the last note is. So, you group ragas of length n into two groups. We have A, those that end a short note. And then you've got the number of spaces to fill up is going to be n minus 1. So we're going to have f of n minus 1 of those. And with a long note, well, then you're going to have a long note at the end here. And you're going to need to fill up the first n minus 1 spaces with something, so you get f of n minus 2. So the way to count the number is just to look at the last note. Well, that's nice. But one thing I realized was I worked with Savage and Herb Wolf, Carlos Savage and Herb Wolf, on another related issue. Namely, suppose that you're an impoverished musician and you just have one piece of paper that you're going to try to use to remember what raga you just played. Then you're going to want to play the next one, but you want to make a minimal amount of changes on your piece of paper. So let's think about, and when I explain how to write down a given raga in an efficient way, and then how to sequence them in a nice way. So, next question. So how to record a raga? So how to record here's the idea. Just record the set S contained in 1 through n minus 1 of positions of the first beat of a long note. Record the set S of positions of the first beat of a long note. Okay? So, we do a little example here. So let's take n equals 3. Ragas of length 3, we've already talked about. You can have one with 3 short notes. There's no long note, so S is n pieces. Okay. Or the other possibility was a long note followed by a short note. So there S would consist of 1. And if you have the last remaining one, then you have a S consists of 2, because that's that's the position of the start of the unique long note. So if you ask yourself, well, first of all, you can't have a long note starting at position n, because it's 2 beats long, so it would go off the end. So this is a subset of 1 through n minus 1, and the main property of it is this. The main property of S
So this set S is all for all ragas you just said.
Yeah, if you look at all ragas of length n, let's write down one of, we want to record one of them. There's one of them we got in mind. One way to sequence these little squares and rectangles. And the way to do it is to say, I'm only going to pay attention to, let's just pay attention to the positions of the long ones. If I know where the long ones are, then I know where all the short ones are. And to say where a long one is, you just need to give the beat where the start of it is. Okay? But the question is, what sets S can come up? I'm saying S is contained in 1 through n minus 1 because you can't start a long note on the nth beat. The long note is 2 things long, so it would fall off the end. You can't do it. But you can start it on the second to last beat, and that's what we had here. So the main property of S is that S contains no two consecutive integers. And that's because you can't, notes are not supposed to overlap. Long notes don't overlap. Another way to say it is, you'll see why I'm saying this. S is two free, meaning that if you take two elements of S and they're different, then the absolute value of the difference has to be at least 2. That's a complicated way of saying there's no consecutive elements, but I have to do that because later on we're going to generalize 2 to 3. So, and furthermore, if you take any set S, then 1 through n minus 1, that has no two consecutive elements, that defines a Raga, because that tells you where you put the long notes. Put the long notes there. You fill everything else up with short notes, and you're done. So what this result about Fibonacci numbers says is that if you look at the number of two free subsets of 1 through n minus 1, that's the nth Fibonacci. But now I want to come back to this question of the poor impoverished musician who only has one sheet of paper to work with. And now, on a sheet of paper, this person can mark down a subset S. Put the subset S in your sheet of paper. And then he says, okay, I've just played this Raga that's represented by S. I want to work my way through all possible Ragas of length n. I want to go from this one to another one by making only one change. I want to add one element to S or delete one element of S. So let me see if I can write that down. Suppose we want to list all possible Ragas. N. In such a way that to go from one to the next, we either add or delete just one element of the corresponding S. Now, actually, what's interesting about this is that this concept came up much earlier. It's called the gray code ordering. So I want to describe a gray code ordering. It came up as signal processing back in the 1950s. A fellow named Frank Gray was interested in listing all subsets of 1 through n minus 1 in such a way that to go from one subset to the next one on the list, you only need to either add one element or subtract one. So let me write down the formal definition of a gray code order.
So when you are subtracting with the corresponding element, that means you are dividing long node into short two.
It means I'm just removing one long node. I'm removing one long node, or else I'm adding one long node. Let me do an example. Maybe I should first give a...
Removing one long one and adding another one long one.
Well, I want to just be able to remove, I'm allowed, if I have a given raga, I'm allowing myself to take out one of the long notes to make a new raga. Or I have my given raga, and then I'm allowed to put in one more long note someplace. That's allowable.
So the length will be different.
Well, I want each long note to have length 2. So to go from a raga with a certain number of long notes to one that has an additional long note, I need to pick 2 consecutive short notes and turn them into a long note. So those are the 2 allowable things to do. Let me write down the definition of a gray code order. Gray code order of a collection S1 through SF of subsets of the integers from 1 to n minus 1, say, is an ordering. S of I plus 1 differs from S of I by adding, that is adjoining, or deleting one element. So let me write down an example here just to make clear what we're talking about. So example. If n minus 1 is 3, okay, then n is 4, and the 2 free subsets of the integers 1, 2, 3 can be listed gray code order by, well, it's not unique, but we can take the set consisting of 2, then the empty set, then 1, then 3 and 1, and then 3. So that's the way to do it. I start with 2, I remove the 2, get an empty set, I add a 1, and I throw in a 3, and then I subtract a 1. So this would correspond to ragas on 4 beats. And so if you were going to actually write out the possibilities here, you'd have, well, let me just do them vertically. Short, long, short. And 4 shorts, and a long, 2 shorts, 2 longs, and then 2 shorts and a long. Okay, so at each stage, either I take a long and convert it into 2 shorts and leave everything else alone, or I take 2 shorts and convert them into a long. That's the only thing to do. Okay, and there's 5, which is Fibonacci. Okay, so the question is, can you always do this? Can you take all of the 2 free subsets of the integers from 1 to n and write them down in gray code order? that would be kind of natural from the point of view of Indian classical music. Because if you're going to play each of these, you think that the next variation that you'd want to make, if it's going to be sort of pleasing, should have substantial overlap with what you did before. Musicians sort of do that. They make a little variation on what they just did. When I was learning the drums as a kid, I mean, they used to have these things called 4-bar breaks. You'd play 4 bars and then you'd play another 4 bars. So the theorem, this is not a very deep theorem, but it's true that for all of them, T sub n of 2 subsets of the integers from 1 to n minus 1. I'm doing this n minus 1 kind of perversely to emphasize that the Ragas have length n can be listed. So I'll indicate a proof and then I'll play it for you in some small example. Well, you think about the Fibonacci sequence. The sketch goes like this. If you take t sub 0, then you've only got one possibility, an empty set. So let's take t sub 1. So this is 2 free subsets of the set with just one element. So the only thing we do here is take the empty set and take the set consisting of one element. Okay. So this is the ordering on the 2 free subsets of the set with just one integer. And then in general, what you do is you say t sub n, this ordering should consist of first taking whatever you were able to find for t sub n minus 1, but you take it in reverse order. The bar means take t sub n minus 1 in reverse order. And then you follow it by the following. Think of it as n tensored with t of n minus 2 in reverse order. So what this means is that you take t of n minus 2 in reverse order and adjoin n to each of these sets. Okay, since it's 2 free subsets of 1 through n minus 2, I'm free to add an n to that, and it'll stay 2 free. So that's it's not so hard to prove by induction that this works. Just for laughs, I tried to see what it would sound like. I tried to look at n equals 8, and I was kind of hoping that it might be interesting, but so did this work? I don't know why the computer is waking up. Oh, here we go. Okay, so I was trying to experiment with this, but I didn't. So this is what it sounds like, roughly, when n equals 8. So it's a little bit boring. Okay, well that takes some work. That's anyway, roughly what it sounds like to play this. It's not exactly the music of the spheres, but it is somehow a canonical sequence of pieces of music. Now, this is all kind of elementary, but what amazed me is when I heard about this. I worked out something with Herb Welf and Carlos Savage that's a little more deep, involving the following variation on this whole scheme. So let's do the following change.
This theorem is about the existence of this listing, right?
Pardon me?
This theorem is about the existence of this.
Yeah, it just exists one, yes. There may be
Many.
there may be many others.
Is there any way to count how many?
That's a great idea. That's a great question. I don't know how many gray code orders there are. That's a wonderful question. That's a very natural question, but I don't know the answer. Maybe there's, what would be the optimal one? I don't know. This is the one that somehow comes from a Fibonacci method, but maybe there's other ones. So here's the variation that I wanted to do. Suppose that we look at, here's another question. What if we say, take some integer, g greater than or equal to 2, and we say, the long note, g times the length of the short note. So for example, for g equals 3, then you're just saying the short notes are still right angles, but the long notes end up length 3. And curiously enough, before I'd heard any of this Indian music analogy, we'd actually thought about this. So the natural first thing to say is that these correspond to G-free subsets. So let me say, make it up. A subset of the integers between 1 and n minus g plus 1 is, say, G-free if whenever you take two elements and they're different, then, well, they have to be different by at least j in absolute value. And it's not a big surprise that these G-free subsets now are the ones that will parameterize or list the ragas using these kinds of notes. So, record that. So, ragas. And native notes. G correspond to G-free subsets. S of these integers. And of course, the correspondence is the same as before. The method is just record the positions on the starting beat of the long notes. So now the question is, can you list these in gray code order? Imagine you want to write down all of these ragas, work through these. And before I ever heard of this in music analogy, we proved that you can't. So let me write down that. Well, the theorem was, this was with Savage and Herb Wolf. Now I'm going to change from n minus g plus 1 just to n because it's confusing. So the statement is that if n is sufficiently large, quantification rates. So if G greater than 2 is given, and N is sufficiently large, where sufficiently large depends on G, then there is no gray code ordering of the set G and G of all G free subsets of the integers from large. So there's no way that you can write all of these Ragas down one after the other with only making one change at each station. And in fact, any subset of V and G, which can be gray code ordered, must miss an exponentially increasing balance. As n grows. So there's no way to do that once the G gets to be larger than 2. So let me give an idea about how this works. I'm not going to go through the details, but I want to explain why linear forms and logarithms actually is important. There's some deep results of Feldman going back to work of Baker in the 60s that this result was. So here's the idea. Okay. Let's suppose that we could do this, or at least that we could take a subset of V and G, for which we can find a gray code order. So suppose V is a subset of V and G. Which has a gray code ordering. Okay, so let's write it down. You take T, and then you say, okay, T1, T2, T3, so on, up to T sub F. Now, each of these successive sets is a subset of 1 through n. But each one differs from the next one just by adding or deleting null. It's a little complicated with this. You've got to keep track of what's a subset of what. So each Ti is a G-free subset. And Ti plus 1 differs by Ti adding or deleting null. Well, a very easy consequence of that is that if you look at the number of elements in T sub I, well, T sub I plus 1 differs from that by either adding 1 or subtracting 1. So we've got a congruence. The number of elements in Ti is the number of elements in Ti plus 1 plus 1 mod 2. So what has to happen here is that in a gray code ordering, you have a sequence of subsets, but the parities of the orders of the subsets flip back and forth, mod 2. So the consequence of that, this is in the transactions. I think if you just do a math size search, you'll find it if you're interested. Well, okay. Then what has to happen is that if you look at the number of elements in this collection, the number of indices for which the order is even, minus the number for which the order of the subset's odd, those two numbers differ by at most 1. So you'd have the consequence is, I say d of b and g was the number of elements of b and g of even order minus the number of elements of b and g of odd order. Well, if these are radically different, then you can't possibly list the thing in gray code order. And more precisely, then a number of things that you miss in your nicely gray code ordered subset is at least equal to the absolute value of that function minus 1. Okay? You have to miss that min. So the whole business now is to try to estimate this number. You could write down that, and you could try to prove it grows exponentially with n, and you've got a result. So let me just sketch a little bit about what goes into that and apply linear forms of logs there. So when you get to this stage in the talk, it's always a question of where you come from, about what you're going to want to talk about. I'm not really a combinatorialist person, so I'll just say use generating functions. Find the formula. Just the same. Just as the nth Fibonacci number can be written down as a linear combination of nth powers of the golden ratio and its conjugate, there's a formula for this that's rather analogous, but I'm not going to write that down. The dominant term well, there's two cases. There's one nice case where it looks like a times theta to the minus n, or two could look like this. This is the unpleasant case. A times theta to the minus n plus a2, I have to be a little cautious here, theta bar to the minus n. Okay. And now I have to say what these numbers are. Theta the absolute value of theta is a root of x to the g minus x plus 1 of minimal absolute value. Its absolute value is actually less than 1. And theta and theta bar are the unique roots. With this absolute value. And I should say something about the constants A1 and A2. So A1, and A2 are non-zero and in they're algebraic numbers in the field that you get by joining these theta and its absolute its complex conjugate. So you can do the calculations and you can find out, looking at the formula for D, B, and G, that you have one of the those two dominant terms. Now the absolute value of theta is less than 1. So when I take big negative powers, I'm going to get a large number, exponentially growing. And in the first case, we win automatically because this is growing exponentially with n. And because it's growing exponentially with n, I get this growing exponentially with n, and I have to miss a large number of things in any great quadratic subset. Now the problem is that this case really happens. You have a situation where you have two different complex conjugate roots. And the issue is, when you look at these roots on the circle, on a certain circle of radius less than 1, could there be a kind of conspiracy for some gigantic value of n that would make this number very small? And that's where linear forms and more come. To show that that conspiracy can't happen, let me show a little bit about that. Just the heuristic idea. Let me just write down what the line here is that Hughes results from linear forms and modes. Algebraic numbers show that in the second case, in the bad case, 2, at least this thing is really the dominant term. You have A1 theta to the minus n plus A2 theta bar to the minus n bigger than C0 of R times R to the minus n for some function C0 of R positive when R is anything bigger than. So the essence of the problem is that this formula for D, B, and G has what are hopefully these dominant terms, but you can't exactly be sure. You have to prove they really dominate the other terms. The other terms come from other roots of that polynomial, and you need to make sure that this one dominates any such term. So what would happen if this weren't true? If we weren't able to prove this kind of thing? True. Well, more like what will happen is that you have to have the absolute value of 1 plus A2 over A1, theta bar over theta to the minus nth is going to be less than some constant here. Where we got C0 bar and 1 R over theta minus n. And how can that happen? Morally, this thing has to be very close to minus 1. Very close, unreasonably close to minus 1. So a little bit of a further calculation ends up with this kind of thing. do a little calculation and you'll get this. You'll get, well, if it's close to -1, then the negative of it should be close to 1. So if I take the log, some complex branch of log up here, with the absolute value of that, I would get this less than some constant, say C1 of R, which is very computable from C0 times R over theta to the -n. And now if you extend this out a little bit, you get a linear form in logs on this side. And on this side, you have an exponential of something that's decreasing. So this is going to be an exponential of minus the log on these logs now of R over theta times n, and then there'll be some little correction back there. So the moral in the form, here you have a linear form in logs of algebraic numbers where you know what the coefficients are. This is not changing with n, and you have n times a log of another algebraic number. And the idea in linear forms in logs is that in order for this to be close to 0, unreasonably close to 0, it has to be equal to 0. That's the essence of the results about linear forms in logs. Linear forms in logs of algebraic numbers, where the coefficients are integers that aren't too large, if they're unreasonably close to 0, they have to equal 0. And so let me finish by saying what the theorem of Feldman is. And then, of course, you have to deal with the case in which that is actually equal to 0, but that's an algebraic number theory problem, which you can take care of. So I'll write down the Feldman theorem. Distinct non-zero algebraic numbers. Okay. And suppose we have some bunch of integers, b1 through bm, and I let h be the maximum of all those. So if my hypothesis is that you have a linear form in these logs that is not exactly 0, so you take some complex branch of a logarithm, and you're taking this linear form in the logs of the algebraic numbers. If this is less than the exponential of some constant times the height of those b's, some delta positive, then h is bounded. By a function of delta and beta and theta. Let's just put it like that. You can be more explicit, but this is exactly what you're going to say. That if you have a linear form in logs that's not 0, then the coefficients can't be too large. In the application, that then bounds n. So for once n is large enough, the corresponding linear form in logs has to be x0 on the nose, so then we get an algebraic relation between these things. And we can apply algebraic number theory to rule that. And so that's how you end up proving the theorem.